To build a modern enterprise data system, engineers have to balance two completely opposing forces: the requirement for processing fast transactional states and the requirement for deep historical analysis on that same information. The first force is online transaction processing, or OLTP. These systems are engineered for high-velocity, short-burst atomic events, like a credit card swipe, an airline reservation, or an IoT sensor ping. The second is online analytical processing, or OLAP. These systems are designed to query massive data sets to identify long-term trends and generate business intelligence. Structurally, you cannot optimize a single database to do both at once. The physics of data retrieval forces a hard choice between high-speed transactions and heavy analytical aggregations. Because no single structure can optimally perform both tasks, engineers must split their architectures, creating the first major divide in enterprise systems. On the transactional side, the engine of choice is the Relational Database Management System, or RDBMS. To handle those rapid transactions flawlessly, an RDBMS uses a strict structural method called database normalization. The goal is to eliminate all data redundancy. Instead of keeping a customer's information in one wide row, normalization fragments it into small, specific tables, one for user profiles, one for orders, and one for shipping, all connected through foreign keys. This rigid structure guarantees ACID compliance. An update made in one location instantly and safely updates the whole system. By ensuring no duplicate records exist, normalization protects businesses from anomalies. For example, it prevents a bank account from showing two different balances in the same database. While strict normalization secures transaction integrity, it creates massive friction for large-scale analytics. Imagine asking a live OLTP database to calculate regional sales performance over the past 5 years. To find the answer, the query must reassemble those fragmented tables using resource-heavy database joins. Scanning across those fragmented tables locks up compute resources. If the database is busy trying to calculate 5 years of history, it cannot process the credit card swipe happening right now. The live environment can slow down or even crash. To protect the live transaction system, organizations physically isolate their analytical data into a different storage structure. This isolated environment is the data warehouse. Unlike the operational database, data inside the warehouse is intentionally denormalized. Engineers reintroduce redundancy to ensure faster read access. The primary organizational framework used in this environment is the star schema. The star schema is anchored by the fact table. This holds the quantitative, measurable events, like transaction amounts or quantities sold. Surrounding that center are the dimension tables. These hold the descriptive context for those facts, things like dates, store locations, and product details. Because the descriptive data is pre-joined to the numerical facts, business intelligence tools can execute massive aggregations across millions of rows without getting bogged down by complex joins. The star schema sacrifices storage efficiency in exchange for faster analytical query speeds. You cannot simply dump raw operational data into a warehouse. The structure is too rigid. It requires a strict governance mechanism to manage the movement.
This is the ETL pipeline: extract, transform, and load. In the extract phase, data is pulled from diverse source systems, like relational databases, simple flat files, or external APIs. In the transform phase, the data is cleansed, standardized, and forced to conform to the requirements of the star schema before it is stored. ETL pipelines act as gatekeepers, ensuring that only high-quality, structured data enters the warehouse. This model worked well until the era of big data arrived, characterized by massive volume, rapid velocity, and a high variety of sources. Organizations began generating petabytes of unstructured data. JSON files, video logs, and sensor streams violate the strict schema requirements of the traditional warehouse. Forcing that volume of unstructured data through a traditional ETL transform bottleneck is slow and cost-prohibitive. The solution is the data lake, a centralized repository that accepts raw data without upfront modeling. This volume forced a change in the pipeline structure, moving from ETL to ELT, extract, load, and transform. The data is loaded directly into the lake first. ELT utilizes cloud computing to transform data on demand inside the lake, only when needed for analysis. The data lake traded the rigid governance of the warehouse for the raw scale and flexibility required to train machine learning models. The data lake introduces a specific risk. Without strict metadata management and cataloging, a lake can quickly become unsearchable and unusable, a state often called a data swamp. Because early data lakes lacked ACID compliance, enforcing data reliability was nearly impossible. You could not run precise financial or transactional reporting on unverified data. The resolution to this tension is the data lakehouse architecture. A lakehouse implements warehouse-level features, schema enforcement, indexing, and ACID transactions directly on top of raw lake storage. This allows teams to run complex BI queries and train AI models on the same unified platform, eliminating the need for costly data duplication. Even with a unified lakehouse, a single, centralized data engineering team inevitably becomes a bottleneck for a large enterprise. This bottleneck led to the data mesh, which moves away from a centralized monolith toward a decentralized ecosystem. Business domains, like marketing, sales, or finance, take over the responsibility of owning and managing their data. This approach treats data as a product. Each domain serves its data to the rest of the company via standardized APIs. The data mesh solves the organizational scaling limit, preventing central engineering teams from drowning in domain-specific requests. As these systems integrate with machine learning, the focus shifts toward data veracity. AI models require absolute trustworthiness to function safely in a production environment. That trustworthiness is managed by the metadata layer, which tracks the context, ownership, and rules for every piece of data in the ecosystem. Metadata enables data lineage, the ability to trace an AI model's output all the way backward, through the transformation steps, to its original operational source. Automated governance tools use this lineage to flag sensitive data, stopping it before it accidentally reaches an AI training model. Ultimately, modern data architecture is the engineered foundation required to turn raw digital exhaust into reliable,